Hey guys, new module, new lesson. Time for us to start talking about LANs, and I figured we would do that on the whiteboard. First and foremost, what is a LAN? Well, a LAN is just a fancy term. Stands for Local Area Network. Now, a local area network is very important for us because it really defines what we clinically refer to as a network in the confines of Cisco's deployments. Now, we can have small networks, we can have large networks. We saw examples of each of those, but let's take into account the fact that in a network, what I would typically have is I would have a switch of some kind, and I would have devices, let's say hosts. Say we have two hosts on this network right here. That's the little keyboards down there. All right, now these hosts would be connected to my switch. I could also have something along the lines of, say, a server. I could have a printer. You know, here's a little piece of paper coming out of the printer. And that's going to define exactly what's involved in a network. Now, recognizing this, what we have to realize also is the fact that this is going to be one particular network. So let's say network A. Now, I mean, I've seen smaller, I've seen bigger, but I've seen huge also. Huge networks whereby we have multiple switches in the infrastructure. So let's say SW1, SW2, SW3. My head's going to become a problem, so I'm going to move over here. Actually, let me do it this way. I'll move over here. And we're going to have even the possibility of having more switches where I can have redundant connectivity between all of these devices such that I have a partial or a full mesh deployment that I'm going to be using for the purposes of my switching. But then what ends up happening is I could have whole offices. So I could have, instead of one computer, I may have 55 here connected to this one. I may have 155 connected here. These are all hosts, by the way. I may have 50 servers connected here. And all, again, bounded together to create this concept of an actual network. And the point being is that these are all going to be typically within the same network segment. Now, bear in mind, it's not until I take my switches in some fashion, shape, or form and connect them to a router that I'm going to get the ability to be able to send information from one of these centers to the other and vice versa. And it's going to be through this idea of deploying this concept of local area networks that I'm going to build these infrastructures. And it's important for us to understand that when it comes to networks, just like when we talked about networks, where we talked about components, we have to recognize that there's also components for a LAN. And oddly enough, since we use the term LAN normally to define a network, you're going to find out that there's going to be lots of similar terms. For instance, we have computers. Now, that means in the confines of computers, I'm talking about hosts, or AKA PCs. I can also have servers in my deployments. And we need to make certain that these devices, so let's assume here is a host, here's another host, and when I go through and I start doing my connections, I recognize now I need to have some way of interconnecting my devices. I mean, that's what this class is all about, right? ICND1, that stands for Interconnecting Cisco Network Devices. Well, how do we do that? What enables that entire process? Well, it's through network interface cards that we get the capability of being able to do it, and media. Now, in the confines of media, what do you mean, Terry? Well, I'm talking about, are we using fiber? Are we using copper? What solutions do we have? What are we actually employing? But it all really boils down to the fact that it's still an interconnecting method, and it's going to also change the rules for us, because that means we're going to have other devices. So not only are there interconnections, we have to understand that there's interconnecting devices. The two interconnecting devices that I want to make certain that we highlight again are the same ones that we've been talking about to date: routers and switches. Now, in the confines of a router, obviously, we've said time and time again that I need to have a router to move information from one network to another network. Switches, however, allow me to connect multiple devices in my infrastructure such that I'm going to be able to have interconnection in the local area network itself, or the basic idea of a network. So when we look at this, the first thought is if I were to do this logically, this host, so host A, would be connected to host B. But again, that's logical. What we actually realize is point of fact, is that there's typically going to be a switch here, and that switch is going to have a connection to host A and its connection to host B, and it's going to transparently afford them connectivity between themselves via this switch. And this is all also going to be enabled by protocols. Well, what is a protocol, Terry? What is a protocol? Well, in the Army, we had protocols that we had to learn. I mean, if you're going to be talking to an officer, there were rules that you're supposed to use to talk to an officer. If you're going to talk to a foreign dignitary, you had rules that you were going to use that would govern how you communicate. And that's exactly what a protocol is. In the diplomatic service, that's what they're referred to, is protocols. So the term is still the same. What are the protocols that we want to be able to interact with? Well, first and foremost, we have to understand that we have different areas in our infrastructure where we're going to have different protocols. So for instance, let's assume we have a router, say R1. R1's connected to a switch. I'll just draw my famous pizza box. I have a physical connection between these two devices. My switch in turn is going to be connected to other components. Let's say I have a host, a computer. Let's say I have a server. And when we start looking at this, what exactly are our protocols? Well, the whole idea here for having a router would be so that I could connect to the internet. Remember, I described the internet as a large inter-area network. Now, we have a couple of ideas that I want to make certain that we bound here. This is our LAN, our local area network. This is going to be an inter-network connection to the actual internet, which is going to be a large interconnection of networks, just like what we're describing. And what we need to understand here is the protocols that we're going to use to communicate. Well, between hosts and our servers, we're going to use both the IP protocol for our logical addressing, and also remember we're going to use the Ethernet protocol for our physical addressing. Remember we talked about ARP, Address Resolution Protocol, which is the protocol that allows me to basically look up an Ethernet connection based on my IP address. There's also another concept you'll hear every once in a while called RARP, Reverse Address Resolution Protocol, which takes an Ethernet address and finds the IP address. Hardly ever see any terms with that anymore. But we've got IP and we've got Ethernet. Other things that we want to talk about are this concept of ARP, Address Resolution Protocol, because it is pivotal and critical for us to be able to understand what's happening in our network, and ARP governs the behavior of how devices communicate on an Ethernet segment. Lastly, what we're going to talk about is called DHCP, Dynamic Host Configuration Protocol. We have an entire module dedicated to it, but what we're going to do is we're going to find that as we start delving deeper and deeper into this concept of LANs and LAN components, it's going to be through the exchange of this information and the use of these protocols that we get particular behaviors. So what is, first and foremost, why do I need switches? So why do I need a switch? Why, oh why, do I have to have a switch? Well, remember, a switch gives me port density. It gives me the capability of connecting lots of devices to an individual centralized point using a star topology. Even though it's going to function as a logical bus, but it's still a physical star. But it gives us other advantages. When I use my little pizza box right here, which is my switch, again, I'm going to have a port going over to a host, let's say host A. I'll have another port over here going over to host B. I'll have a third port over here going down to host C. Now, the important thing that we want to understand is first of all, I get the capability with a single device to be able to support all of these components on a single switch. We can find switches anywhere from 8-port switches to 12-port switches, 16-port switches, 24-port switches, 48-port switches, 96-port switches. So you can see, then there are others, but as you can see that we get a lot of range as far as the ability to be able to support lots of users on a single device. But we also get something else that's really significant to us. Now I'm going to grab my eraser here and see if I can't take this out neatly. Probably should have drew that somewhere else. So looking at this, we also get another benefit. Now remember, I said routers allowed us to communicate between networks. Switches are basically the boundary elements that define networks. They also do something else for us. Remember I mentioned CCNA, Carrier Sense Multi-Access Collision Detection. That used to be the go-to tool to prevent devices from trying to communicate simultaneously across an Ethernet wire. Now, the benefit there is that it stopped collisions, or prevented collisions, or allowed us to have a back-off algorithm to recover the possibility of a collision. A collision being where host A and host C start talking at the same time. They send voltage down the wire. The voltage doubles since they're operating at the same time on the same circuit. And the system would say, oh no, you guys can't talk at the same time. We had something referred to as a skip algorithm. The skip algorithm would send instructions to the different hosts to step back and wait a random period of time and then try to retransmit. The problem was the bigger our layer 2 infrastructure on our Ethernet got, the more probability and the more catastrophic collisions became. So what we wanted to do is we wanted to be able to implement a way to be able to prevent collisions, and we do that through the concept of switching. Because what we're going to do here is we're going to have other things that we need to know. So for instance, routers break up broadcast domains. So Terry, what's a broadcast domain? Well, let's cut over to another whiteboard and let's look at what a broadcast domain is. A broadcast domain means that if host A sends information via broadcast, which means we have unicast, uni meaning one, so it's going to be one-to-one. So host A can communicate to host B, and vice versa. We have multicast communication, which means host A can communicate to devices, let's say B, C, D, where host A could send messages to other devices that are listening to a specific multicast address, whereby C, if it wasn't listening for it, would not be burdened with the traffic. So here we have one-to-one, here we have one-to-N, or one-to-many, and then lastly we have broadcast. Broadcast traffic is going to be where I have the same scenario where I have A, B, C, and D, and I send it to the broadcast message. It goes to every device on my network. Now at first blush that's great, but what if I have 255 devices on my network? That means I'm going to be sending that broadcast information everywhere in my infrastructure. What if I had 16.3 million devices in my infrastructure, something that's supported by what we'll talk about later on called a Class A address? The whole notion here is again, it's going to go to everybody, which means again, it gives me the problem where things can start seriously bogging down. So what we want to do is we can use a router to break up our network into smaller broadcast domains. However, a router does nothing to the other element that we need to discuss, which is called a collision domain. Let me get myself out of the way here. A collision domain. A collision domain is exactly what I was describing before, where we use CCNA to be able to detect a collision and back off from it. So every device that was in the collision domain had a chance to collide by sending information with all of the other devices that were part of that domain. And in the early days, that was on an individual Ethernet segment when we had things called hubs. Then what we got switches, this bad bear right here, the pizza box. The switch allows me to absorb collisions. Well, what does that mean? Well, it means where a router breaks up broadcast domains, a switch breaks up collision domains. So how does it happen? Well, it happens by the switch absorbing or buffering the packets that are being sent. So every one of these ports will be in a different collision domain. So when we go through here, we may have one unified broadcast domain. So where the black dotted line is the broadcast domain. So if host C sends something to the broadcast, it's going to go everywhere except for the port that it came in on. It won't go back out that. That's going to be a loop prevention method. But what we're going to see here quite literally is that by virtue of the fact that this is a switch, it's going to take information, and if there was traffic, say for instance coming from host C, what's going to happen is the switch is going to wait until the line is clear to send it. So what it does is it actually buffers the information coming from the hosts, thereby preventing the possibility of collision. And it's going to no longer use collision avoidance. So it's not going to use CCNA CD anymore, because a switch actually has the capability of being able to absorb inbound packets and waiting until a more timely period to be able to send the information through. Now, the last part, or one of the last parts that I want to cover here, is going to be the fact that we have to look at how our switches operate. So switches provide specific functions. So let's entertain what those are. Let's look at what the functions of a switch are. So when we come in and we start looking at it, what's going to happen is it's basically going to provide four functions. Function 1. The switch is going to operate at the link layer, and it's going to operate at the link layer to support the TCP/IP suite. So again, the switch is going to provide services to the next higher layer in the TCP/IP model, or even in the ISO model. All right, next what we're going to do is it's going to have a special job. That special job is going to be to forward, filter, or flood. And what's it going to forward and filter? What's the PDU at this level? It's the frame. So it's going to forward, filter, or flood frames. And it's going to do all of this based on MAC addresses. Now, what do I mean by that? Well, I mean, quite literally, switches have tables. Those tables record MAC addresses. MAC addresses that are assigned to frames that have been sent or exchanged based on the source. So when we look at how switches operate later on in ICND2, we're going to find out that these switches construct these tables. But the point is that if a switch receives a request to communicate with a MAC address that is not in its MAC address table, then it's got a job to do. And that switch is going to say, well, what I'm going to do is if I have 7 connections and I receive a request for a MAC address on this port, what's going to happen is that it's going to say, I'm going to flood that request out all of these ports. Now, it will not forward it out the port that it arrived on. Again, it won't send it back down the port that it arrived on to prevent the possibility of a loop. And we'll talk about how loop avoidance takes place in layer 2 very shortly. But the main thing that we need to understand here is that this is going to be that flooding process, because switches will flood unknown unicasts. So if it doesn't know the MAC address, It's going to treat it as a unicast message that is unknown, which means it's going to go through this flooding process. Now, what we see here is that it's going to, first of all, send it out all of those interfaces. The other thing is it has the capability of being able to drop those frames, or it has the capability of just simply forwarding them on. If I know the MAC address as a destination, then I will forward that frame on. So looking at it that way, just in a nutshell, that's what's happening with regard to our switches. They can forward, filter, or flood. And then the other thing is that we have to recognize here is that the switches, because of the fact that they buffer, well, let me use a better word, because they create separate collision domains. So if I have a 196 port switch, that means I have 196 collision domains. So none of those 196 hosts would have the capability of colliding with each other and being able to create a problem on my network segment. So by breaking it up into collision domains, the other thing is that our switches give us the capability of supporting the concept of full duplex speeds. Well, what do I mean by full duplex? Well, we have simplex communication, and then we have duplex communication. Simplex means communication can only take place on the segment in one direction at a time. So I send, then I have to wait before I can actually receive. Full duplex uses a different set of rules. Because I'm buffering packets, I can actually support the concept of sending and receiving at the same time. So let's think of this as being able to do that all simultaneously. And the other and last component that switches give us is it gives us the capability of being able to support variable speeds. So the idea is that you go to the store and you buy a 10 megabit network card, take 10 megabit. Then later on you go get a 100 megabit card. Then later on you get a 1 gig card. Well, by virtue of the fact that I have a host with a 100 megabit, a host with a 10, and a host with a 1 gig, all connected to a switch that is going to be able to understand 10/100/1000, what ends up happening is the switch allows these devices to all communicate. That is one of the primary and key benefits that switches give us. Now, I mean, that's a lot. That's a lot to absorb. And you guys may want to actually stop this, go back and listen to it again. But these 4 elements are critical to building a modern network infrastructure. Without switches, we would be in the Stone Ages. We would have major issues because we would not be able to support things like VLANs, which we're going to talk about shortly. We would not have the capability of being able to integrate multiple speed environments. We would not be able to have full duplex operation, which means we would lose almost half of our high-end layer 2 features. Now, the benefits also to this is the fact that a LAN switch, in my topology, my LAN switch is a 3560. I actually have some 3550s. These are just old end-of-life switches. You may have 3750s, which are newer. But the main thing here is that these switches give me the capability to support, like I said, high port density. Like anywhere from 8 all the way up to 96 ports on a single device. Gives me the capability of supporting frames through the concept of buffers. Remember, it's absorbing the possibility of a collision and then sending out the frame at a more adequate time. The whole concept, like I said, the mixture of port speeds. The other thing is that we have what's referred to as hardware optimized switching. Hardware optimized switching allows these switches to work at wire speed. So a router does everything using the processor in some degree. It has no real hardware optimizations to be able to support high-speed switching environments. Our hardware switches operate using a concept called distributed switching, where they have something called an ASIC, an ASIC. That stands for Application Specific Integrated Circuit. Now, ASICs are basically small mini computers that are associated to the ports or groups of ports on our devices that allow us to be able to take functionality, like switching, and offload it from the CPU of the chassis such that the ASIC can step in and take care of all of those responsibilities and move information around and act as the go-between for all transactions between hosts and the switches, between switches and other switches, or even switches and routers. So that allows our devices to work at wire speed. So if I had a pure 1 gig switch, that means every port could function at 1 gig. And then the last thing here is money. I mean, I remember when I was working for, I think it was BB&T back in the day, they bought a switch. Actually, they brought a bridge. It was a 2-port switch. It was 15 grand. And now I've got 24 ports and 48 ports in my rack here that I used to study for my CCNA that cost me $250. So as you can see, the big thing here is that from the point of view of cost is the fact that we get high port density, but we get it at a low cost. And that is absolutely invaluable when it comes to creating a modern infrastructure. Because again, most of our deployments are going to be restricted and broken up on the basis of cost. So, I mean, anytime the boss has got to whip the wallet out and start paying for stuff, that's when people start taking a critical eye and looking at whether or not it's absolutely needed. And the fact that our port density costs are so low in these switches, and the fact that they operate at line speed and they give us such a boost in capability in our local area network, our LAN, which is going to be an individual network, one of possibly many, but that payoff is going to make certain that we get all of the infrastructure and services available to our users when and where it's needed. So, with that being said, I hope this was helpful, and I'll see you guys in the next lesson.